Hello Internet, my name is Quinn and this is Blondihacks. Now, this is a non-locomotive week, so that normally means I'd be working on the tool sharpening system in this slot. However, I've got a little bit of a side quest to do. I got kind of a rush job, or what counts as a rush job in this little shop, and I'm going to make what's kind of known as a wheel of fortune or a lottery wheel or a raffle wheel. You know, those things you spin with the little ticker on them and you win prizes, door prizes, that kind of thing. I got involved with a local community group here and they wanted such a wheel for little fundraisers at farmers markets, that kind of thing. And it was a really interesting engineering challenge to figure out how to build one of these things. So we're going to do that and then I'll be back to the tool sharpener soon. So let's go. I'm going to make this thing out of steel because of course I am. Have you seen steel? It's awesome. I've got a whole bunch of it on my rack that I pulled down. I think I can make it entirely out of these pieces that I have lying around. I want it to be steel also because it'll be heavy so that you can really rip on it. It's not going to move around. And there's some safety reasons as well, which I will get into later in the process. I think this piece here will give me the wheel. I want the wheel to be somewhere in the like 7 to 12 inch range. So let's start there. I'm going to center punch a mark there. And I'm going to trace out what I think is a good diameter for this thing. It needs to sort of sit comfortably on a desktop and be easy to transport around, but still big enough to be fun to spin for adults and kids. This big piece of scrap is much too big for any of my bandsaws, so it's over to the least civilized form of metalworking, the angle grinder and a zip disc. It's loud, it's messy, but it gets the job done when all else fails. Plus you get the obligatory slow-mo and hard rock spark footage that every YouTube video seems to require. Then I can cut close to my line on the bandsaw. If you're wondering how I'm going to get this perfectly round, well, I was wondering too, but I knew I was at least going to have to rough cut it close to my line. Getting it perfectly round with the machine tools that I have is going to be an interesting exercise because of the size of this thing. But regardless of the method for truing it up, the closer I get rough cut to the line, the less work I'll have to do on whatever machine tool ends up doing this. Since we're about to move to the civilized metalworking tools, I'm going to clean it up now, get all of the oil and crud on it that's still there from the steel yard, or more likely the scrap yard where I got it. I actually like having the crud on it when it's sitting on the shelf because it keeps it from rusting, but when I actually want to work with it, I want it to be clean. I'd like to true it up on the lathe, which I could theoretically do on my faceplate. My lathe has the swing for it. However, I know from experience that at this diameter, my lathe doesn't have the torque required for turning steel. Even aluminum at the full swing on my lathe is kind of a challenge, so I'm almost certain that's not going to work. Another option then is the rotary table on the mill, and this will work for a larger diameter as long as the overhang off the edges of the rotary table is not too much. Now I do have quite a bit more than is ideal. I've got a couple of bananas all the way around of stick out. The rotary table I have is actually not that big. However, odds of success are a lot higher than on the lathe, I think. So I'm going to try the rotary table first. I will need a center hole to start with, so I'm going to do that on my drill press since I've got space on the table for it. I'll line that up with my wiggly center pointer thingy-majiggy. This doesn't have to be perfect because we're going to be truing it up anyway. It just has to be close enough so that I have enough material to clean up. I'll clamp that down with my float lock vise. One of the less sung features of the float lock vise is the fact that you can clamp flat things down to the table with them. One more reason that everybody should have a float lock vise on their drill press. If you'd like one of your own, I did a 4-part video series on making this one based on drawings that a friend of Mr. Pete's drew up and released to the public, so awesome project. I drill out that center hole and now I can take it over to the rotary table and start getting set up. I made keys for the bottom of my rotary table so that getting it installed straight with the x-axis of the mill is trivial. It's one less setup step. Setting up rotary tables is quite a lot of work, so anything you can do to reduce it, the better. And that includes this Morse taper mandrel that I made that goes in the center of my rotary table. And that gives me a center fixturing point for work, but also gives me an easy way to center up the rotary table on the spindle. That's the other very time-consuming part of rotary table setups. This allows me to put a little plug in the spindle and line up the center by feel. This is not as accurate as dialing in the center of the table, but it's accurate to within 1,000th or two. Next, I'll bolt the center hole into the mandrel that's in the center of that table. Now that mandrel does not have a drawbar in it, it's just the Morse taper stiction holding it in there, which means you can't over-tighten the bolt, or this happens. It just pops the mandrel right out of there. It's fine for light-duty work, and this is just a temporary hold, but I do have to be careful not to over-tighten that. But I only need it long enough to get a second fixturing hole in there that allows me to then use the T-slots on the rotary table. Now, a reasonable question would be, why didn't you drill that first fixturing hole over on the drill press so that you'd have it here? Then you could use that to hold it securely to drill the other 3 fixturing holes. There's a very subtle and sophisticated high-precision reason that I didn't do it that way, and that's because shut up, that's why. Once that first T-slot hole is in place, though, the other 3 are easy because now the plate is held more than sufficiently securely. I don't have to worry about that mandrel popping out anymore. As you can see, I'm very carefully lining up each hole with the location of the T-slots on my rotary table so as not to drill into my rotary table, which would make me very sad. I like this rotary table. I don't want to drill holes in it. And since someone's going to comment on it, yes, I know those T-nuts are a little on the small side. I made them for a smaller rotary table than this one, but they still fit, all right? Just back away slowly from the caps lock key, sir. Now comes the less fun part of this process, turning the OD of this plate. I move the x-axis over until I touch off on what I believe is the high spot of this, and then I run it all the way around. I'm keeping an eye on the gap between the cutter and the plate, so I can crank quickly during the spaces where I clearly have a lot of room, and then I slow down when it looks like it's getting close, so I don't jam it into the cutter at too high of a feed rate. But eventually, after enough passes of chipping away at the high spots, I get fairly continuous cuts in most of the areas around the plate. Now, this looks quick and easy on camera, and in your mind, you might be thinking turning an OD on a rotary table is easy, but this is actually quite slow, and it's tricky to get just the right feed rate, and you are also fighting a little bit of chatter because the large plate has a lot of leverage on the rotary table, and so it wants to kick back a little bit. I am conventional milling, not climb milling, but still, you do get a little bit of counter-rotational force on that plate. So you have to crank just right. I've got a little bit of tension set on the table locks to help counteract that chattering potential, and made my way all the way around. This cut took about an hour. On the lathe, it would have taken, 18 seconds, and the resulting cut is actually not quite as good as the lathe would have done. Rotary tables are awesome, and when you need one, they are just the thing. But for basic turning operations like this, they aren't as concentric as the bearings in a lathe are, and while it does work for this, it's not really the ideal tool for the job. But any port in a storm, and it allowed me to get this thing done, and actually that surface finish is pretty nice. So at the end of the day, results are results. We got it where we needed to be. Now I'm going to drill a bunch of holes all the way around the edge for the little pins that you hang onto when you spin the wheel, and also these pins are what the little ticker arrow thing rides on. I'm going to support the edge of the plate there with a machinist jack because I'm drilling, remember, way out in space. Again, I've got a couple bananas that stick out off the edge of the table, so that material is going to need support. This is the plus side of doing this on the rotary table, of course. After turning that diameter, I don't have to move anything. I'm already all set up to do a whole bunch of angular and rotary features that I need on this wheel. So in the end, I think I did actually probably save time by doing this all on the rotary table. So, I might have sounded like I was throwing shade on rotary tables there, but I'm not. They're awesome. And in this case, I think it was a good choice for all of these steps, including the turning. I drilled and reamed all of these holes because I want an accurate dimension. I want the pins to be a very close slip fit in these holes because I'm going to Loctite them in place. That will save me having to do a bunch of complicated threading or fasteners or snap rings or something else to retain the pins in the table. If I get a really accurate fit on the pins, then Loctite is all I'm going to need. I chose that method because I knew I had this piece of 304 precision ground stainless on the rack. I'm going to be able to make pins from this stuff that fit really accurately in those holes. I cut a bunch of lengths of this from the bar, and I'm going to clean up all of the ends over on the lathe. I'm not exactly sure what length I want for these yet, but I'm going to start by cleaning up and lightly chamfering both ends of each, and I brought all of the pins down to the same length, kind of eyeballing what I thought might be a good length for a Raffle wheel pin. I don't know, I've never made one of these things before, so I don't know what's going to look and feel right yet. I wanted to make those pins now, though, while the plate is still set up on the rotary table, so that if I need to do an oversized reamer to make those pins fit the way I want, I still have it set up to do that. I didn't want to tear down the setup until I had the pins in hand. But in fact, The regular nominal size reamer was just right. That pin is a perfect fit in there. It's like a friction slip fit, which is just the right clearance for Loctite 680. And it feels like a good length to hold on to. And I think that's going to be a nice length, actually. I mean, I don't think it matters a whole lot, but that feels good. While I had it sitting here, I had the idea to maybe engrave the wedges right on the wheel. I thought that would look really cool. I have this 2-flute carbide chamfering bit, but it has a split point geometry on it, so in theory it should be able to engrave. I'm doing a very light cut on a piece of scrap that I clamped to the top of the disc just to test out that theory, and indeed, that made a really nice engraved line. I don't think you could go very deep with this. This is a little bit abusive on this tool, I think, but this actually worked really well, so I went for it. This was slightly scary because I could trash the entire part with this move, but I mean, it looked really good on the scrap, so what the heck. I decided where looked about right visually for each line to end. I marked that position on DRO, and then I just ran it all the way down the piece until that stopping point. Then cranked around to the next position on the rotary table and did it again. I had decided ahead of time that about 8 wedges looked good, so that's the angles that I'm using. Now you'll notice that I had to remove one fixturing screw on every other line. Mea culpa, my intention was actually for those fixturing holes to land in the centers of wedges because the centers of the wedges are going to be covered in the final piece, as you'll see. However, when I started drilling the pinholes around the edge, I kind of forgot and I ended up with the fixturing holes between the wedges. So they will be visible in the final result, but they'll just be speed holes. I suppose I could try to weld them up and grind them flat to make them disappear, but with my welding ability, I'd probably just make it worse. When those lines were done, I thought, it would look really cool if they were all connected with a center ring. And it was all set up already on the rotary table. DRO and everything tells me exactly where to go, so I went for that too. It's amazing how sometimes as you're working on something, ideas just fall into place and everything comes together. I didn't really plan any of this. I was just winging it as I went along, and the result, I think, is actually really nice. I'm very pleased with that. I need to think about the center bearing now. I do want to put a real bearing in the center so it'll spin nicely. I went over to the bearing corner of my hardware drawers. I knew I had a bunch of extra ones lying around. And I went through the various options just looking for something that felt about right size-wise. And I kind of landed on this one on the left. This is actually an ABEX 7 bearing. I think it's a spare one that I bought for my D-bit grinder and it turned out to be the wrong size. So this will be the world's only Raffle wheel with a surface grinder grade bearing in it. Hey, if you're going to do it, ridiculously overdo it. I'm going to get that hole started with a pilot point drill because I need to start with as large a drill as I can to save myself boring head time, but I don't want to use a regular chisel point drill because I don't want to drill into my rotary table. So I want to be able to drill like a flat bottomed hole, if you will, so I can stop just at the bottom of the plate and not risk touching the rotary table. I think the bore in my rotary table is big enough for this drill, but I don't know for sure, and I really don't want to mess up my rotary table. I got away with that though. I didn't touch the rotary table. I had more clearance in there than I thought, fortunately, so that's enough to get me started with the boring head. And then with the boring head, I know how thick the plate is, and I've got my quill DRO, so I can just stop a few thousandths short of the bottom of the hole, effectively leaving a really big burr at the bottom of the hole, but guaranteeing that I won't touch the rotary table, even if I do get into an area that's larger than that center bore. Fortunately, I don't have too far to go here. I just need to get to the center diameter of the bearing because there's going to be an axle that goes in this hole. The standard fit for any bearing is that one or the other, the inside or the outside, is a press fit and the opposite surface is a slip fit. So I'm going for a slip fit on the axle, and then the outer bearing will be a press fit in the frame. That looks good. I think we're there. And just to cross-check with a different method, I've got this piece of scrap that happens to be a perfect fit in the center of that bearing and is also a perfect fit in this hole. So, job done. I'm finally done with this rotary table setup. I gotta say, this worked really well. It was definitely, I think, a good call for this part, as tedious and annoying as the turning portion of it was. I think that turned out nice. This was a little bit of a deburring challenge because of those engraved lines. A very shallow machined feature is tricky to deburr. What seemed to work best was a Scotch-Brite wheel on the Dremel combined with some cold chisel work along the surface. I tried bright boys and scrapers and various other things, but that was what seemed to work in this case. And I think that turned out nice. Those engraved lines really, I think, tie the room together. Next, onto the axle. I found this piece of scrap, which is sort of in the ballpark of a Raffle wheel axle, so we'll start with this. It does have a hole in the center of it that is going to cause us a little bit of trouble, but I want to use up this scrap because I have it, and we can kind of work around that hole. I actually do need a hole in the center of this axle anyway, but as you can see, the one that's there is off-center. It's running out quite a bit. However, as I said, we can work around that here shortly. I'm going to start by turning the OD facing the end, all the usual shenanigans. Now, the first feature that I need is a shoulder on the front of this. The idea is that there's going to be a flange on the front of the axle with a little shoulder that sits inside the wheel, and there's a bolt on the front that clamps the wheel against that shoulder, and then that shoulder sits against the bearing. That spaces the wheel off of the bearing a little bit and gives me something to clamp the disc to. You can see what I mean here. When I put the disc on, see how the end of the axle is a little below the surface of the disc? So now I'm going to be able to clamp the disc to that with a bolt in the center. To turn the area behind the shoulder that sits on the bearing, I'm going to use a grooving tool so I can do it all in one setup. I don't have to flip the piece around this way. I'm going to run the grooving tool in behind the flange that I want. I'm going to stop a few thousandths short of final depth, and I'll do a series of plunge cuts all the way down to remove the material in this area. Doing this with a grooving tool is a bit of a time-consuming way to create a diameter, but it allows me to do it all in one setup, so I get perfect concentricity all the way down, which is, important in a spinning axle, of course. On the final cut, I go to full depth, and then I sweep across to even out the surface. If there's any errors in the grind on the end of my grooving tool, this will cancel out those errors. And coincidentally leaves a really nice surface finish. You can actually turn longitudinally with a grooving tool, as long as you take very light cuts. If you stay within the nose radius on the corners of your grooving tool, then you can turn just fine. And in fact, you get a really nice cutting action. It acts very much like a shearing tool, which was a old school tool used like in the 19th and early 20th century for getting good surface finishes. So there you go. That's why you read the old books, because for manual machine tools, the information in them is still good. And of course, break all those sharp edges. Next, I need a snap ring groove, and that's going to hold the axle into the bearing. It's going to hold the bearing up against the back of that flange. For the geometry of this, I went to Machinery's Handbook. For a given size of snap ring or E-clip or any other fastener, Machinery's Handbook will tell you exactly what all of the geometry of the slot should be. Really helpful. Hopefully now you can see how this all works. When the disc is on there, then the bearing will be in the area right behind this flange here, and the snap ring is going to hold it all together along with a bolt on the front. Speaking of that bolt, I want to use this hole on the front to tap the threads, but of course that hole is running out a lot because I didn't dial in that stock in a 4-jaw, which would have been a lot of work. Instead, what I'm going to do is just remove that hole with a 2-flute center cutting end mill in an end mill holder in my tailstock. And this can mostly gain concentricity back. It is going to wander a little bit. A 2-flute cutter can't create perfect concentricity the way a single point cutter can, but it removes 90% of the runout in that hole, and that's good enough in this case. I've thus effectively removed that off-center hole completely from the part, using an end mill that's smaller than the tap drill size that I actually want, and now I can come back in with that tap drill, and it's as if I had drilled a hole on center to begin with. You can see a teeny bit of wobble in that drill because, as I said, the end mill can't perfectly remove an off-center feature, but pretty close. Another way to do that if I needed the concentricity to be perfect would be to drill it out a little more to make room for a boring bar, a very small boring bar, and then bore it out. But as I said, didn't need that much concentricity, so the end mill did the job a lot easier. And then of course, in we go with the parting blade. Break the sharp edges because chamfers are what separate us from the animals, and Yahtzee. There's the completed axle, pretty pleased with that. Sometimes the most engineering goes into the smallest parts. Time for a quick dry fit. So the axle is a really nice slip fit in that bearing. It's tight enough that it's not going to spin in the bearing, but it doesn't need to be pressed in. Then the shoulder on the axle goes into the hub like so. And then I'm going to temporarily bolt this in with some washers, but I'll make a nice looking center hub for this towards the end, as you'll see. But for now, I'll bolt this in place to give it a little test. I'm not going to bother with the snap ring, but I can see that the groove is in the right place, so this should work just fine. And look at that. It's actually got a surprising amount of momentum. Turns out 10 inches of 1/8-inch steel plate, pretty heavy. Inertia is a real thing. That is going to spin for days if you really rip on that. Should be actually lots of fun to spin. Next up is a frame that's going to hold that bearing. So back to my scrap. I've got, I think, one flat section over here that should be just big enough that I can still squeeze out of this really warped piece of stock. That little piece right there should actually be a nice stand for the back of this wheel. Many years ago at a scrapyard, I got a very good deal on this piece of steel because it had this big bend in the middle of it. Nobody else wanted it, but I knew I could get a bunch of projects out of it, and here we are 10 years later, very gradually working my way around the bend. I'm keeping things fabricator level square, but I'm not machining every edge of every piece on this. That kind of precision just isn't necessary here and would take a lot of time. I want to do a neat job of it, but let's not go crazy here. I do want to put some nice design detail into it, so I'm going to put a peak at the top of the frame, which will allow the pointer thingamajig to kind of peek up from behind the wheel. And all of these edges are getting finished on a combination of the belt sander and the Scotch-Brite wheel, just to clean up the rough saw cuts and burrs and so on, so everything is nice and soft to the touch, but again, not worried about everything being machinist straight and accurate. I need to punch a big hole in the center of this thing now for the bearing, so I'll start by laying that out and marking where I want that to go. This needs to be very accurate because, again, I want this to be a press fit on the bearing, so I'm aiming for a 1/2 thou interference fit. To get myself close, I'm going to go into my drawer of shame where everything goes that doesn't fit somewhere else, and somewhere in this sad collection of hole saws, there should be something that's close but not over the size that I need. And indeed there was a pretty good match. So in we go. The trick to hole saws in steel is to run them slowly. That's a big diameter cutter and your surface speed has to be right just like any other cutter. So this is, I think, 250 RPM, which felt about right. But I gotta say, these Milwaukee, #not-sponsored, bimetal hole saws are the business. Boy, they do a nice job. I just punched a hole the size of a baby's arm in 1/8-inch steel plate in about 9 seconds. Not very many ways that you can do that. Now, it's not a machinist grade hole, it's not going to be super round and the finish in it may not be great, but as a starting point, hard to beat. I do need a machinist quality hole here, however, so I got to finish up with the boring head. Recall that there's going to be a bearing pressed into this hole, and press fits are where precision really, really matters. They got to be just right, or you'll damage things, or you won't be able to press it in, or you'll get it halfway in and it'll get stuck, or even worse, it'll be too loose and then you're toast. So precision, really, really important. Taking my time, taking light cuts, managing deflection because boring heads have a lot of that, and just making sure that I really nail this dimension. Quick sidebar, because I get asked this a lot. The way you get good results with these cheap brazed carbide boring bars is you have to put negative rake on them. Because just like any other cutter, that top surface is the cutting surface and that has to be on center. And because the brazed carbide is so thick on these things, you have to angle it backwards to get that cutting edge on center. People think those boring bars are no good. They work just fine, you just have to set the cutting edge on center. And on center by eye is close enough. On to the measuring now. I'll make sure I did this right, using my telescoping bore gauge for an accurate measurement. Good technique with these is important. I did a video on how to use these tools. If you're interested, check out my Mill Skills playlist. Now, let's see how we did. Oh, look at that, son! That is how it's done. Blind squirrels and nuts and all that, but that is an exact 1/2 thou interference on an 1 3/8. When you've been doing this for a few years, you get to where you can kind of feel interference fits, and when I put that bearing in there, I can feel that like it wants to go in, like it's almost thinking about forming a committee to start going in, and that is what a 1/2 thou interference feels like. So that is perfect. Unfortunately, that is all the time I have this week, so I'll leave you with some cool spinning. Thank you very much for watching. I hope you've enjoyed watching this so far. Lots more to come on this project. It's going to get really cool, I promise. Thanks to my patrons for keeping this whole shenanigan going, and I will see you next time.